Hello everyone, my name is Tejas Bhansali and today we will discuss the numericals on Rankine cycle. In the previous video, we discussed about the basic layout of thermal power plant, its PV and TS diagram. So if you haven't watched those videos yet, please go and watch them. And if you haven't subscribed to my channel, please subscribe to it for more such interesting videos. So let us start today's video. First numerical, the steam power plant operating on ideal Rankine cycle, the superheated steam enters the turbine at 3 megapascal and 350 degrees centigrade pressure. Condenser pressure is 75 kPa. You have to find out the thermal efficiency, and this is the given data. You can take the screenshot of it. Now let us plot the TS diagram for the processes. And this question or similar type of question was asked in GATE 2016 exam. Let us plot it on TS diagram. You can also plot on PV diagram or TS diagram, anyone. For sake of convenience, we will plot on TS diagram. And here you have to find out the thermal efficiency of cycle. So 1 to 2 is isentropic expansion in turbine, then there is the condensation of steam, then pumping and heat addition in boiler. Okay, the formula for thermal efficiency is work output, which is turbine work minus pump work, upon heat added, which is in the state of 1 to 4. Okay, now the question arises, how did I take steam condition at turbine exit as wet steam? Okay, we will see it further. Before that, let us find out enthalpies at point 1. At point 1, as you can see, there is a superheated vapor at 3 megapascal pressure. So at 3 megapascal, the enthalpy is directly given as 3115.3 kilojoule per kg. So H1 is its enthalpy or specific enthalpy at point 1 is 3115.3. And also now process 1 to 2 is isentropic. As you can see, there's isentropic expansion. So S1 will be equal to S2. Now S1 is also given here at 3 megapascal pressure. The entropy is 6.7428 kilojoule per kg Kelvin. So S1 will be equal to S2 because of isentropic expansion, 6.7428. Now comes the question, how did I take the state at point 2 to be wet steam? So check for Sg at 75 kilopascal. So as you know, Sg is equal to Sf plus Sfg. Okay, Sf at 75 kilopascal. At 75 kilopascal, Sf is 1.213. So 1.213 and Sfg. Sfg is given as this is Sfg 6.2434, and adding these two terms, you get Sg is equal to 7.4564. Now at point 2, actual entropy is 6.74, but for saturated steam it would be 7.4564. Okay, as this S2 is less than Sg, so you can see that S2 is 6.7428, but Sg is 7.4564, and therefore S2 is less than Sg. Therefore, point 2 will have wet steam. Had these two been equal, it would have been again dry steam. Or if this S2 would be greater than Sg, then it would have been superheated vapor. But as of now, S2 is less than Sg. So point 2 will have wet steam. So for that, you will have to find out the dryness fraction using this formula. S2 is equal to Sf2 plus X2 Sfg2. S2 is 6.7428, Sf2 is 1.213, Sfg2 is 6.2434 at 75 kPa pressure. Okay, and on calculating this, we get X2, that is condition of steam at turbine exit as 0.8857. Now you can find out the enthalpy. H2 is equal to HF2 plus X2 HFG2. So enthalpy, putting the values given in the question, you get H2 as 2402. Now H3, which is the condition of steam at exit of the condenser, always it is the saturated liquid. So look in HF at 75 kPa in steam table or in the given question. HF at 75 kPa is given as 384.39 kJ per kg. Now here you have to take the pump work also into account. So pump work is, as I told you in the previous videos, it is the product of pressure limits and specific volume. Specific volume at 75 kPa, because pump works at between points 3 and 4 and the pressure is at point 3 is 75 kPa. So that's why you have to take Vf at point 3, which is given as 0.001037 into pressure limits. Pressure was 3 megapascal, converted into the kilopascal, which is 3000 kilopascal minus 75 kPa. So pump work is 3.03 kilojoule per kg. Now pump work is H4 minus H3. As you can see here, pump is between point 3 and point 4. Applying steady flow energy equation between these points for a pump, you will get pump work is equal to H4 minus H3. So putting the values, you get H4 as 387.42. Now efficiency is work output upon heat added. Work output is turbine work minus pump work. Because why the minus sign? Because we are supplying the work to turbine, and if work is supplied to system, it is negative. That's why I have separated it from the turbine work. And this is the heat added. Now heat addition take place between points 4, 5 and 1. So net heat added will be H1 minus H4. Again using steady flow energy for boiler. Okay. So by putting all the values, you get the efficiency or thermal efficiency of the plant as 0.2601 or 26%. Now let us see the Rankine cycle with some modification. The first one is Rankine cycle with regeneration. Similar type of question was asked in GATE 2015 exam. So the question statement is: steam enters a well insulated turbine and expands isentropically throughout. At an intermediate pressure, 20% of mass is bled to the feed water heater for regeneration, and remaining expands isentropically at 9 kilopascal. Neglect the pump work, and this is the given data for turbine inlet, intermediate and at turbine exit. Okay. Now first of all, let us understand what is the feed water heater using the TS diagram. Now let us try to understand the process based on TS diagram. So first two is, there are two turbines in the process, HPT and LPT, high pressure turbine and low pressure turbine. So at 1 to 2 this isentropic expansion in HPT, high pressure turbine. M1 is the mass flow rate. Now after coming to this point, the part of steam goes in feed water heater and remainder goes to LP turbine. Now what is this feed water heater? Let us understand. Now basically the feed water heater is a heat exchanger consisting of a tubes through which the feed water flows. Now the bled steam is passed over these tubes, where it condenses and transfers its latent heat of vaporization to the feed water flowing in the tubes. Okay. Now the amount of steam to be bled is such that it is just able to heat the feed water up to saturation temperature of blade stream. That is, it becomes saturated liquid at pressure P2 given by point 6, as you can see at in this point. Okay. By doing so, there are two advantages. Number one, thermal efficiency of the plant will increase and there will be less amount of thermal stresses to the boiler. But the limitation is that it will increase the cost of the plant. So in this case, we have to find out the turbine work output by neglecting the pump work. Okay. Now again, in the question, it was mentioned that at point 1 and point 2, the steam is superheated. Now, and nothing was given about point 3. So let us find out steam condition at point 3. As you see, you can see that 1, 2, 3 is an isentropic expansion process. So S1 equal to S2 equal to S3, which is 6.6, which was kilojoule per kg Kelvin given in the numerical statement. Now checking Sg at point 3. So Sg is given as 8.1 kilopascal, sorry 8.1 kilojoule per kg Kelvin at 9 kPa. You can see in the question given. Again Sg is more than S3. So steam is wet steam. So if the steam is wet, you have to find out the dryness fraction by using S3 is equal to SF3 plus X3 SFG3. S3 मतलब pressure at point 3 or at 9 kPa. Entropy S3 is 6.6 kilojoule per kg Kelvin as found above. SF3 is specific entropy at point 3 or at 9 kPa for SF3, or for pure liquid is 0.6. X3 you have to find out, and SFG3 is, as you can see, that Sg is equal to SF plus SFG. Okay, Sg and SF are given in the numerical question, and you can easily find SF by Sg is 8.1, SF is 0.6. So Sg is X3 is 0.8. Using this equation, you can find out dryness fraction at 0.3, that is at exit of LP turbine, which is 0.8. Use these two equations to find out. SFG and HFG exactly on the similar lines. H3 enthalpy at this point. It is HF plus X3 into HFG3. HF 174 क्वेश्चन में गिवन है. HFG3 इज Hg माइनस HF, ये भी क्वेश्चन में गिवन है. सो H3 इज इक्वल टू 2094 kilojule per kg. Now work output from turbine, and mind you, you have to find this in megawatts. So it is M1 into H1 minus H2 plus M3 into H3 minus rather H2 minus H3. Now you are given that mass flow rate at entry of HP turbine is 100 kg per second, and 20% of the mass is bled for feed water heating. Therefore M1 is 100, M2 is 20%, 0.2 into 100, 20. Therefore M3 will be equal to 80 kg per second. Putting the values of M1, M3, H1, H2, H3, and therefore you will get the value of WTS work output from turbine as 125,560 kilowatt, because enthalpies are in kilojoule per kg and this is in kg per second, so this will be in kilowatt divided by 1000 to get the megawatt. So answer is 125.56 megawatt turbine work output. Okay, now the last case is Rankine cycle with reheating. Now the question was asked in GATE 2014 exam. Only I have changed the values of all three questions. So reheat Rankine cycle operates between the pressure of 8 megapascal to 10 kilopascal with reheating be done at 4 megapascal. The temperature of steam at inlet of both turbine is 500 degrees centigrade. And you can see the data as enthalpy of exit of HP turbine is 3185. Enthalpy at exit of HP turbine is, rather LP turbine is 2247. And enthalpy at pump exit 191 kilojoule per kg per Kelvin, means at 0.6. Okay, and this is a table given to you. Find the cycle efficiency by neglecting the pump work. So H1, again let us explain the process. H1 to H2 is the HP turbine, isentropic expansion in HP turbine. Then before passing to the condenser, it will go to the reheater, which is installed between these HP turbine and LP turbine. So before going to condenser, first it will go to reheater where the steam will be reheated, and then again expand in the LP turbine, and then into the condenser, then pump and boiler. Okay, now here all the values at all states are given, so no need to worry about the state of steam at point 2 and point 3 or point 4. Everything is given, every value of enthalpy is given in the example, and you have to find out only the thermal efficiency of cycle. The thermal efficiency of cycle is work output upon heat added. Now work output is how much? Here there are two turbines, so it will be H1 minus H2 plus for HP turbine, and for LP turbine it's H3 minus H4. So H1 plus H2 plus H3 minus H4. I have got these equations by using steady flow energy equations. Now upon heat added, it is number one is H1 minus H6 in the boiler, and another heat addition takes place at point 2 to point 3 in the reheater. So H1 minus H6 plus H3 minus H2. This is the expression for heat added, and this is the expression for work output. Now by substituting all the values, H1 is 3399 kJ per kg, H2 is 3185. H1 मतलब enthalpy at exit of HP turbine. Sorry, H1 is what? Enthalpy at entry of HP turbine, which is 3399. Steam enters at 8 megapascal, 8 MPa. That's why 8 MPa में enthalpy is 3399. So 3399. Enthalpy at exit of HP turbine is 3185. So H2 is 315. Enthalpy now at 4 megapascal, and is at 0.3. 4 megapascal पे enthalpy is 3446. So H3 is 3446 kilojoule per kg. H4 means exit at LP turbine. So at exit of LP turbine, the enthalpy is 2247, and enthalpy at pump exit H6 is given as 191 kilojoule per kg. Okay, so by putting all the values, you get the thermal efficiency of cycle as 40.73%. So I hope you understood all the numericals, and that's all in this video. See you in the next one. Till then, like this video, share this video, and subscribe to my channel. Thank you.